Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. In this video, we're continuing our discussion on radicals. And in this video specifically, we're going to be talking about rationalizing the denominator. If you want to follow along with this and the notes in written form, as well as examples, you can follow along with it on page 70 of my book, Algebra in Words 2, which you can find at on Amazon, and the link to that is in the description box below. So first, let's talk about rationalizing the denominator. What is it and what does it mean? Well, basically, when we report a final answer, it's a standard way of reporting that we do not leave a radical in the denominator. And beyond that, that's the best I can tell you. But what we want to focus on is strategies to basically keep the value of a fraction the same, but basically manipulating it so that there's no radical remaining in the denominator. And there's a couple easy methods that we're going to look at to do that. Now, just to categorize, there's two different types of radicals that you'll be dealing with, fractions with radicals. One is when there is only one radical in the denominator, or what we call a monomial. That would be like the types that I have on the board. There's types with one term in the denominator, and then there's also times when there are multiple terms. Really, you'll probably only deal with binomials with radicals in the denominators. I'm going to show how to simplify one term in the denominator first, and then we'll look at how to rationalize a denominator with a binomial with radicals second. So anyway, let's get started. Let's start with this fraction, 1 over the square root of 3. Now, I'm just going to show you right away what to do. We're going to multiply the top and bottom by the square root of 3. And why is that? Well, for these, I like to work from the denominator up, because really the denominator is the focus. Now, if you remember from any of the previous videos, when you multiply a radical, a square root times itself, it equals the base. So the square root of 3 times the square root of 3 equals 3. That's in the denominator. And just to clarify again why that is, we go back to this principle, which I have written here. When the root is the same as the power of the base, it equals the base. And remember that you could move the power outside of the radical as well. It's the same thing. Finally, 1 times the square root of 3 in the top is just the square root of 3. So our final rationalized answer is the square root of 3 over 3. And you might notice the square root in the numerator, but that's okay because we're rationalizing the denominator, getting the radical out of the denominator. And it's fine if it lands and ends up in the numerator. Now, before we go to the next example, I want to further clarify the method that we used in the first example, because it's not always as easy as just multiplying the radical times itself. Let's look at this one. 1 over the cube root of 5. Now, if we were to multiply the cube root of 5 times the cube root of 5, what we would actually have is 1 over the cube root of 5 squared, not cubed. So in that case, this would be 3, and this would be 2, and they don't equal, so therefore we would not get rid of the radical. That's why I have these examples here, because the better way to look at it is you want to multiply a radical that's standing alone times itself, the same number of factors, basically one less number of times as the root. So for example, suppose this was over 1, but it doesn't matter. Suppose it was the 7th root of x. And the question is, what do we have to multiply the 7th root of x times to make it x? Well, the answer is the 7th root of x, the number of factors, so that when this plus this are added, they equal the root, which is 7. So if this represents the 7th root of x to the power of 1, and we multiply it times the 7th root of x times to the power of 6, 1 times 6 is 7, and then the root, that I show that here, and then the root and the power are the same, and then they equal x. Likewise, suppose we started with the 9th root of x, and we had to multiply the 9th root of x times something to get x. The answer would be multiply it times itself 1 less time than the root. 1 less than 9 is 8. So if we multiply the square root of 9, the 9th root of x times the 9th root of x 8 more times, 8 times the unwritten exponent of 1 is 9, and then the root and the power are the same, and then it equals x. So if you need to, pause the video a second and just look at the pattern between this one and this one, and then you may recognize why we were able to multiply this one times the square root of 3, because the same principle applies. It's set up so that the root and the power are the same, and then the radical goes away and you're left with just the base. Now let's apply this whole principle to this example where the denominator is the cube root of 5. And the question is, what do we multiply the top and bottom by? If we learn from these examples, we're going to multiply it times itself 1 less number of times than the root. So multiply it times the cube root of 5, and 1 less than the root 3 is 2. And make sure you do the same to the top. The same that you do to the bottom, do to the top. Which is the cube root of 5 squared. Now if we take this down, let's multiply the top, which is just going to be the cube root of 5 squared. And then in the bottom, we're now going to have, if you add unwritten exponent 1 with power of 2, 1 plus 2 is 3, and then we have the cube root of 5 cubed. And now, since the root and the exponent are the same, we can eliminate the radical, and it's just 5, the base, 5. And in the top, it stays what it is. So, starting off with 1 over the cube root of 5, when we rationalize the denominator by multiplying the top and bottom by the cube root of 5 squared and simplify, we end up with the cube root of 5 squared over 5, and the denominator has been successfully rationalized. Now these two examples are representative of rationalizing a denominator with one term. I'm going to pause the video and put a couple more examples up where we're going to look at rationalizing the denominator for binomials, and the method is going to be a little bit different. I put 2 more examples on the board, and notice now that the denominators are binomials. Now before we start, and since the denominators do have radicals, we do have to rationalize them, meaning manipulate them so that by the final answer or the final form, there are no radicals in the denominator. Now this is the strategy that we're going to use for that. It's very easy. You're going to multiply the top and bottom by the conjugate binomial of the denominator. That's all you have to do. Beyond that, you just have to do the proper multiplication, meaning foiling it if necessary or distributing if necessary, and then combining like terms. And that's pretty much it. To review multiplying binomials with radicals, I went over that in the last video, multiplying binomials with radicals. And as I also told you in that video, that leads into this. And that's what we're going to do now. So let's let's start with the top one. What I always recommend is to put any binomials in parentheses. So let's do that. Not essential, but I think it's helpful because we are going to be multiplying by binomials. Now, if we look at the denominator, the square root of 3 plus 2, what's the conjugate of that? It's the same terms with the opposite sign in between, which is the square root of 3 minus 2. And what you do to the denominator, do to the numerator. Square root of 3 minus 2. And now we're just going to multiply. It doesn't matter if you do the top or bottom first. I'm going to do the denominator first because it's just the focus of the problem. Now remember, since we're multiplying conjugates, we can apply the special case shortcut to that, meaning you only need to multiply the first terms and the last terms. The square root of 3 times the square root of 3 is 3. And 2 times negative 2 is negative 4. You can continue that simplification on by doing 3 minus 4 as negative 1. And I put that here in the next step. Now let's go to the top. We are now distributing square root of 3 through the binomial quantity square root of 3 minus 2. So we just have to multiply those terms appropriately. And let's start with the square root of 3 times the square root of 3, which is 3. And then square root of 3 times negative 2 is just negative 2 square root of 3. And if we could simplify anything in the top, we would, but we can't. Please keep in mind that you cannot combine the 3 minus 2 here because these are not like terms. This term has the radical, this one is just the number. So leave them as is. You could look for a greatest common factor, but in this case they don't have that either, so just rewrite it. 3 minus 2 square root of 3. Now since we only have a negative 1 in the denominator, we could clean this up by moving the negative up to the top and distributing it to each term. So the best way to answer this question and to leave this form is move the negative up to the top and think of it as distributing it through and changing the sign of each. So negative 3 plus 2 square root of 3. And then we can get rid of the 1 in the bottom because anything over 1 is itself. So this is the best form of that answer. Now let's look at the next one. And the principles are basically the same. The only difference between this example and the previous example is that in this example there's now 2 radicals in the denominator. But that really doesn't make much of a difference. We're going to apply the same method, which is multiply the top and bottom by the conjugate of the denominator. Let's put that in parentheses. And what is the conjugate of square root of 8 minus square root of 7? It's square root of 8 plus square root of 7. So let's multiply that times the top and the bottom. And now let's apply the special case shortcut of multiplying conjugate binomials in the bottom. Product of the first, square root of 8 times square root of 8 is 8. And square root of 7, I should say negative square root of 7 times positive square root of 7 is negative 7. And 8 minus 7 is 1. We could write the 1 for now. And then in the top, we only have 1 times the top, and we could just rewrite the top because it's multiplied by 1. Write it there, I'll write it here. And because it's over 1, we can just get rid of the 1 in the bottom. That's pretty much all there is to it. It does get a little more complicated when there's more numbers and variables involved. So I'm just going to pause this video and put 1 or 2 more problems on the board just to get a little more practice. I put one final problem on the board. And if you take a look at it, you might notice that the top and bottom happen to be conjugates of each other. But basically, don't pay any attention to that. That's just coincidence, and that's not going to play any role in the problem. All we really need to know is that there are radicals in the denominator, and it's a binomial. So the strategy is to multiply the top and bottom by the conjugate of the bottom only. But we're going to multiply the top and bottom by the conjugate of the bottom. And the conjugate of the bottom is the square root of x. Since this is plus, the conjugate is going to be minus 2 square root of y. And multiply the same to the top. I just want to remind you that the focus is this. So we're multiplying the top and bottom by the conjugate of this, which is this. Don't be compelled to multiply the top by the conjugate of the top. That has nothing to do with it. The focus is the bottom. So anyway, let's apply our shortcut product rule for multiplying conjugates. Product of the first, the square root of x times the square root of x is x. And the square root of 2 square root of y, 2 square root of y times negative 2 square root of y is going to be negative 4y. And let's just clarify why that is. Make sure that you multiply the coefficients first. 2 times 2, or negative 2, is negative 4. And then the radicals. The square root of y times the square root of y is y. That's where that comes from. And then in the top, we're basically going to FOIL it. Now, if you remember and you want to apply the concept of a binomial squared, that's what I'm going to do here with you, only to reinforce the shortcut rule for multiplying a binomial squared, because it is important to use and to remember. So the shortcut rule for multiplying a binomial squared, and it is a binomial squared because this and this are the same, is start by squaring the first term. So x, square root of x squared is x. And by the way, if you FOIL this, that's fine. And actually, because it's written in expanded form, I'm going to FOIL it. So to reiterate, square root of x times square root of x is x. I don't want it to be confusing. Then the product of the outside. Square root of x times negative 2 square root of y is going to now be negative 2 square root of xy. And in this case, I'm using the product rule for exponents. Since the roots of the radicals are the same, I can combine their radicands together by multiplying them, which just becomes the square root of xy. But you will notice that that probably will play a role in the next step when we can combine like terms. Now let's do the product of the inside. Negative 2 square root of y times square root of x is going to be negative 2 square root of xy. And now product of the last. Negative 2 square root of y times negative 2 square root of y. Do the coefficients first. Negative 2 times negative 2 is positive 4. And square root of y times square root of y is y. Now, in the row below, let's see if we can combine any like terms. First we have x, and there's no other like terms with that, so we're going to rewrite x. But the middle terms are alike, which is what we would expect because we are multiplying a binomial times itself. So add or combine by the coefficients. Negative 2 plus negative 2 is negative 4. Square root of xy. And just to reiterate and just to extra clarify, these are like terms because they are like radicals. the square root of xy is the same, they have the same root and the same radicands, that makes them alike, that's how we can combine them. And then we have plus 4y, and there are no other like terms with that, so we rewrite 4y. Then in the denominator, we have x minus 4y. Now, before we conclude the problem, you should be looking to see if there's any other way to simplify in the top and bottom. That's just a good rule of thumb. The answer here is no, but I also want to point out that, just to remind you, if you're compelled to see the x and the x over the x and cancel them out, remember you cannot do that right now because there's other terms and pluses and minuses involved. You would only be able to do that if they were factors factored out, but that's not the case. So in short, this is the final answer. And yes, it may look a little ugly considering what we started with, but the point is that we've successfully rationalized the denominator because in the final form there are no radicals in the denominator, and we did do it properly. So anyway, before I conclude, I want to say how this is going to apply into the next lesson. In the next lessons, we're going to be taking a look at taking the square root of a negative radical, which means getting into imaginary numbers. And once we have imaginary numbers, we're going to be getting into complex numbers. I'll explain that more later, but in short, when we have an imaginary number in the denominator as I, that also constitutes a radical, and we will need to rationalize that as well. So we will be using these methods as well to rationalize any denominator or fraction that has I in the denominator. We'll cover that in the next video. But until then, thanks for watching, and I'll see you in the next video.